There, can folks in the chat hear me okay? Can anybody in the chat hear me? Thanks. Okay, so as always, remember to do the seating survey today. The small group activity is due today at 5 p.m. At 5 p.m., the quiz on the activity will release, and that will be due tomorrow at 5, as is the homework for the week is due tomorrow at 5. Next week is going to be entirely about exam review and answering any questions anybody has about the exam material. I have not had a chance yet to make the decision on shifting the dates on the midterm. I had mentioned that the usual list of dates, which would be essentially Thursday evening through Sunday evening, is kind of eating into the Thanksgiving break timeframe, and it was expressed on Piazza that some people would prefer for the exam to be available earlier rather than extending into the break. So what I am thinking of doing is shifting it so that it releases on Wednesday at 5 and then will be due Saturday at 5. If this would be an inconvenience to anybody, please let me know, because I don't want to make a change like this and that be a problem for somebody. Do we have any logistical questions before we get started on some content? No? Okay. So there weren't very many questions on Piazza for live Q&A that had not already been answered well or correctly on Piazza. So I picked out 2 of them that seemed as though they had not really gotten good answers yet on Piazza, and I'll go over those. And then after that, we can open up questions to pretty much anything we want to people want to talk about. So the first one was talking about using Q in problems for dealing with precipitation. So here's an example of that. Suppose you have Ag3PO4 solid, and the dissolution reaction goes to 3Ag plus and PO4 3 minus, and we are told that the concentration of the silver plus ion is 6.3 times 10 to the negative 5 molar, and that the KSP for this reaction is 9.1 times 10 to the minus 14, and that the units on that would be molar to the 4th. And the question is a precipitate going to form at this in this situation? So the first thing to remember is, what is Q? Q is the reaction quotient. So remember that when we define the equilibrium constant, so in this case KSP, it is the silver plus concentration cubed, the phosphate concentration to the first power, and there's nothing in the denominator because there's nothing on the left-hand side that has a concentration. But this is only true under equilibrium conditions. If you have conditions that are non-equilibrium, we call this same set of concentrations Ag plus cubed, PO4 3 minus, the reaction quotient. And so what we do is we determine what Q is relative to the equilibrium constant, and that determines whether the reaction is going to shift towards the products, shift towards the reactants, or not shift at all. So in this particular case, we are told that the silver concentration is 6.3 times 10 to the minus 5. And from the wording of the question, I'm assuming that the only source of silver is from the dissolution of silver phosphate. So that would mean that the phosphate concentration would be related by the stoichiometry here. So if our silver concentration is 6.3 times 10 to the minus 5 molar, molar Ag plus, then from this stoichiometric ratio we have, for every 3 moles of Ag plus, we have 1 mole of PO4 3 minus. And remember, molar is moles per liter, and so we're going to leave the per liter the way it is. So this is converting to molar of phosphate. And so we end up with 2.1 times 10 to the minus 5 molar in the phosphate. So now we calculate our Q. Q is going to be 6.3 times 10 to the minus 5 molar cubed times our phosphate concentration, 2.1 times 10 to the minus 5 molar. And without even necessarily multiplying this out directly, we can see that 10 to the minus 5 cubed is going to be 10 to the minus 15. We have another 10 to the minus 5 here, so we're looking at something that's going to be around 10 to the minus 20 molar. So this is in fact going to be smaller than our KSP, right? So when the reaction quotient is smaller than KSP, Q is smaller than KSP, remember that this is products over reactants, even though we don't really have reactants as part of it in this. And so in order for Q to approach KSP, it has to get bigger, meaning that you have to increase the concentration of the products. And so looking at our reaction, that would mean more is going to dissolve. This means that if this is our concentration of silver, then we are not at saturation. There is not enough silver phosphate in this solution for it to have reached saturation. Does that approach there make some sense? I think so. Okay, any questions on this idea of using the reaction quotient to determine whether you're at saturation or not? Okay. The other question that I pulled off of Piazza was also dealing with solubilities and was trying to understand the difference between a KSP and a molar solubility. So the question here is what's the connection between them? So molar solubility is talking about how many moles of the solid will dissolve per liter. So let's look at that with this same example that we have. So we have a KSP of 9.1 times 10 to the negative 14th, and we have 3 silver ions and 1 phosphate ion that's formed from this particular dissolution process. So for every mole of Ag3PO4 that dissolves, we get 3 moles of silver, 1 mole of phosphate. So we can say that, assuming that this is the only thing that's going to be dissolving, then if we dissolve X here, we get 3X and X here. And so our KSP is going to be 3X cubed times X, or 27X to the 4th. And we have our KSP value of 9.1 times 10 to the minus 14 molar to the 4th. So we take our 9.1 times 10 to the negative 14. Need my calculator. If I can find my calculator. Where's my calculator? There it is. So 9.1 times 10 to the negative 14th. We're going to divide that by 27. So x to the 4th equals 3 times 10 to the negative, looks like 15 molar to the 4th. Now we take the 4th root of that. So the 4th root is going to be 2.4 times 10 to the minus 4 molar. So the KSP tells us the equilibrium constant for the reaction. Now, it's important, the reason this is particularly valuable is that if you have some other source of silver or you have some other source of phosphate, then the KSP can account for that, because it will account for the Le Chatelier's principle of shifting the equilibrium back towards the reactants. But if you are looking at a solution where all you're doing is dissolving one thing in it, then the more convenient way to express that information is the molar solubility, which tells you how many moles of silver phosphate can dissolve. And as you see, the numbers are very different here, because here we have the concentrations to the 4th power because of the way the equilibrium constant is structured. And here we have just a single concentration, because we're talking about the concentration of the solute, of the solid as it dissolves. Okay, there's a question from chat. Is it not saturated? If it is not saturated, does that mean it will not precipitate? Yes. So at saturation, you are at the limit of solubility, meaning that any excess solid will be, any excess solute will be present as the solid. If you do not have enough solute to reach saturation, then there will be no solid and therefore no precipitate. Okay, so does this distinction between the KSP and the molar solubility make some sense? Yeah, okay. All right, so those were the 2 questions that I pulled off of Piazza that did not seem to have good answers yet on Piazza. So the others seemed to. So I am happy to open the floor to any questions about any of the material, either from people here or people in the chat. What do people want to know about? How's everybody feeling about the group activity? So I went through quite a bit of it in class yesterday. So if you do get stuck on some of it, that may help to go through that. I'm also happy to go through specific parts of it right now if people would like more help on it right here. So it depends on what people want.
In your last lecture, did you cover
Question which?
Question 18.
Question 18. Let me pull it up and remind myself of which one is question 18. Let's see. Okay, whoops. Question 18. I talked about it a little bit, yes. So let me switch over to the PC and I will share screen with the Google Doc here. So the idea is that in questions 5 and 6, you calculate the same thing by two different methods. You first do it by an ICE table, and then in 6, you do it by the Henderson-Hasselbalch equation. And you either get the same answer or you don't, and you will either determine that one of those methods is easier than the other or it's not. And so because of that, you will then end up deciding which of these methods you particularly prefer to use. And so question 18 is simply saying whichever approach you want to use, the ICE table or the Henderson-Hasselbalch equation, you do that. And what you're doing is the phosphate buffer instead of what you did up above, which was the bicarbonate buffer. Now, in the phosphate buffer, there are 3 separate reactions, and you have to determine which of them is the one that is active. That is the point of questions, let's see, 12 through 16, through 12 through 17, is to determine which one is the active one. So let's take a quick look at that. And let's talk about the phosphate buffer. So phosphoric acid is H3PO4. We'll say aqueous. So how do we write the standard acid reaction for this compound? What do we react the acid with in a standard acid reaction? With water, that's right. When an acid is acting as a Bronsted-Lowry acid, what does it do? It donates a proton, that's right. So if we look at this compound and we say that in the process of this reaction is donating a proton, the result of it has to be the same thing, missing a proton. The only place that proton can go is to the water. So what does that become? H3O plus, the hydronium ion. So that is the standard acid reaction for phosphoric acid. The dihydrogen phosphate that is formed is also acidic, so we write the standard acid reaction for this as well. So H2PO4 minus aqueous plus H2O liquid, equilibrium with this same thing minus another proton, HPO4 2 minus aqueous plus H3O plus aqueous. The hydrogen phosphate that we generated here is also an acid. So we can write its standard acid reaction. And the method we use is identical. We are told that we have pKa's for each of these. Let me pull those up. So that was given back in question 12. So the pKa for the first one is 2.14. The pKa for the second one, so let's call this pKa1, pKa2, is 7.20. And the pKa for the third one, pKa3, is 12.37. So some advice that I gave yesterday was, upon reading question 12, which says that we have a triprotic acid and we are given the pKa's for three separate, for each of the deprotonation steps, even before I read what the question is asking me about, I start writing things like this down. And in fact, I would go even further and say, what is the Ka expression for each of these? Just so that I have the information in front of me. And so now I have all of the information that we know about these three reactions all in one place. And I can refer to it throughout any of the following questions that we're going to be doing. Now, in that question 12, we were asked which of these deprotonation steps is the important equilibrium in the pH of blood. How do we go about figuring that part out? I'm sorry? Sure. So to ask the question again, the pH of blood is 7.4. Which of these equilibria is the important one at the pH of 7.4? Ka2, because this is the one that has the pKa that's the closest to the pH that we're operating at. Now let's think for a moment about why that is. Remember when we introduced the titration of a weak acid, we had a shape that looked something like this, right? We have our equivalence point here. So for acetic acid, this was around 8 point something. I don't remember what, like 8.2 maybe. And at the half equivalence point, where we go halfway back here, we are in the middle, middle of the buffer region, where concentration of HA equals concentration of A minus. And at that point, the pH equals the pKa of the acid. So the idea is that the region around, the region where the pH is close to the pKa of the acid is the buffer region. So in this case where we have a triprotic acid, so we've got something that's going to look like that. So we have one equivalence point here, we have another equivalence point here, and then another equivalence point out here. We have one buffer region here, a second buffer region here, and a third buffer region here. And so in this buffer region here, we have the pKa 2, and our pH is close to that. So this is the region that matters in terms of the equilibrium that's going on. So the second deprotonation is the one that is going to have a roughly equal balance of the two species of the phosphate that are involved. So in question, need to find it. In question 13, you found that ratio of the two. In question 14. In question 15, you determined the actual individual concentrations of those two. And then in question 16, you demonstrated that the remaining two concentrations, this one and this one, are so small that they can be neglected. Okay. So that's the setup for getting us to question 18. Okay, so all of that information is what leads us to question 18. Question 18, which is the one that we were asking about, is saying to do the same thing we did in question 5 or 6 for the phosphate buffer. And remember, what we did in questions 5 or 6 was to take our lemon juice analog and pump it directly into the bloodstream in the form of a bicarbonate buffer. Here we're doing it not with the bicarbonate buffer, but with the phosphate buffer. So if you decide that what you are going to do is use the ice table version, then you set up an ice table for this reaction using the starting concentrations that you have for the hydrogen phosphate and the dihydrogen phosphate that you determined in questions, I think it was 14 or 15. And the starting concentration of hydronium ion as the amount of the diluted lemon juice that you determined way back in question 4, I think. If you decide, and then you do a shifted initial condition state and you go through and do the calculation. If instead you're doing the Henderson-Hasselbalch equation, then you set up pH equals pKa plus log base 10 of A minus over HA. Now, you have the pKa, that's your 7.2. Log base 10 of the A minus concentration and the HA. So in this case, the A minus concentration is going to be what you calculated from the HPO4 2 minus from the earlier step. And the HA is the H2PO4 minus that you calculated back, I think this was question 15. Yeah, 15. But we have to as well take into account the extra acid that we added. So we have to modify these two concentrations. And the way we do that is that we assume that the extra acid we added reacts with the base to form more of the acid. So if X is the concentration of, well, let's just say the hydronium ion concentration that you calculated way back in question 4, then we are taking away this, the hydrogen phosphate, because it's reacting with the hydronium ion, so minus X, and we are adding it to this, plus X. Now, X is not a variable you're solving for, it's a value that you got back from question 4. And so now you are taking the log base 10 of these modified, these shifted concentrations in the Henderson-Hasselbalch equation. Does that general approach make some sense? Yeah. Okay. And so then the rest of the questions that follow is really just analyzing the magnitude of the result you get here compared to the magnitude of the result you got from the bicarbonate buffer case. Any questions on question 18 here or the lead up to it? More in depth on question 16. Sure, let's see which one that is. Okay, so question 16 was, how do we determine these two concentrations that we have here? So You have already determined in question 15 this concentration in red and this concentration in red. Are you comfortable with getting that information? Okay. So if you have that information, notice that this is the same as this, and this is the same as that. Okay? So that means in this expression down here, you have Ka, 3. You have the hydronium ion concentration because you know the pH. And you have the denominator because you got it from the previous question. So there's only one value left to get. Up here, you have Ka1 because you can get it from the pKa1. You have the hydronium ion concentration because you have the pH. And you have the dihydrogen phosphate concentration because you determined it in the previous question. So the only thing left is this, and you can solve for it. Does that help? Okay. So this is why I'm recommending that when you are seeing a problem where it seems like there's a lot going on, write everything down right at the beginning, because your answer is probably in that information, and you need to just identify, what do I know, what do I not know? And one way to do that would be to mark the things you know like this, or maybe even have a highlighter or something, run yellow over the things that you know. And then you can slowly work your way towards the pieces of information that you are trying to get. So someone in chat says they're having trouble with 17. So was the assumption you made in question 15 that the only 2 phosphate species with meaningful concentrations were the 2 you focused on in question 13 a valid assumption? So what that's doing is it's saying, look at these 2 concentrations here, and then compare their magnitude to these 2 concentrations here. If the concentrations in green here are measurable within, compared to these 2, if it's like 5% of these or 10% of these or something like that, then completely neglecting them may be a problem. But if these are like 0.01% of these or even smaller, then neglecting them to determine these 2 concentrations is probably an okay thing to do. That's the general idea for analyzing 17. And the answer to that depends on the values that you get in these cases. So, if you get, since the total concentration is, if I'm remembering correctly, like 12 millimolar, 1.2 millimolar for these. So say it's like 0.6 millimolar and 0.6 millimolar. If you find that these are like 0.1 millimolar, then we really shouldn't have ignored them. But if we find that it's like 10 to the minus 9th millimolar, then yeah, these can be ignored with no problem at all. All right, any other questions on the group activity at this point? Okay, any questions on anything? Buffers, titrations, coupled equilibria, Le Chatelier as part of coupled equilibria. Henderson-Hasselbalch versus ice tables. Everybody's good? All right, well, I mean, we can make today a short class if that's what people want to do. I don't have anything invested in keeping you guys sitting here. So one thing I will say, I will suggest, is that when we introduced titrations, all of the examples we did were an acid that we were adding base to, so that we were starting low and going high in pH. It's probably a good idea for you to think about and be flexible enough to be able to think about going the other way around, so that you're adding acid to a base, which would be the standard way to do it if your base were the unknown that you're dealing with. So there are no new concepts involved in doing that. But you do have to sort of keep track of, am I dealing with the concentration of hydroxide, or am I dealing with the concentration of hydronium? Am I looking at a pOH or a pH as you go through? And that's something you need to keep track of regardless of which way you're going. It's just that the answers to those questions will be the opposite if you're doing the titration the other direction. So do keep that in mind and probably think about that some. All right, well, thank you, everybody. Have a good day. The test is not written. Yeah. Yeah, that's going to be today and tomorrow, I think. So, yeah. So I will, as soon as I have, I should be able to put up the sort of topics list this afternoon. And I should be able to get the equation list, the equation page up as well this afternoon. And then as soon as I have a better sense of sort of what kinds of questions they're going to be in the kind of the structure, I'll post another one of those, what we know so far on the exam posts. We are not going to have a system sheet this time due to popular demand. And there's not going to be anything having to do with needing Excel to do anything. That was a failed experiment on my part. So hopefully it will be significantly more straightforward to handle. Yes, I would imagine that I would give you a titration curve and have you maybe identify parts of it or read some information off of it. I may have you calculate some points along a titration curve for given combinations. Yeah. So yes, yeah. The biggest issue doing it the other direction is that you don't really have an analog for like polyprotic weak bases. You know, polyprotic weak acids is definitely a thing, and you can have the multiple humps, but there's not really a base that's the same way. So, you typically only have a single buffer region as you're titrating into a base. I'm actually not doing much with that right now. I'm in the process of shutting down my research program. Yeah, because I've decided I want to focus more on teaching. Definitely. Yeah, I found that when I had too much to do, the research would slide, but I'd focus on I'd get all the teaching stuff done. And that kind of tells me something about where my heart is. So I should start listening to that.